In this video we are going to be solving problem 5.23, which deals with flow through a converging diverging nozzle. In this problem we're flying at an altitude of 18,380 feet and we're asked if a shock will occur, and if so, where will it occur in this fixed converging diverging nozzle. And we know that it has an exit area of 4,500 square inches, a minimum area of 4,000 square inches, an upstream total pressure coming into our nozzle of 10 psia, and an upstream total temperature of 1600 degrees Rankine. And we're told that the nozzle efficiency is 0.97 and to use a specific heat ratio of 1.35. Our first challenge will be figuring out which flow regime we're in, whether the flow stays subsonic throughout the entire converging diverging nozzle, whether it's accelerates to the sonic condition at the throat of the nozzle and then continues accelerating in the diverging section to the supersonic case, or whether there is a normal shock in the somewhere in the nozzle or at the exit, and then whether there could be oblique shocks at the exit or expansion waves at the exit. So in order to figure this out, we need to determine our boundary cases. So we want to know what sort of pressure ratio would we need if we were going to have a fully subsonic flow, and what sort of pressure ratio would we need to have a fully supersonic flow. And then based on how that lines up with our actual exit pressure, we will figure out whether or what flow regime we're in from those dividing points. So to begin with, we need to calculate our area ratio. So we know that the area at our exit, A8, is 4,500 square inches. That's our area at the exit, 4,500 square inches. And we're looking actually here for the ratio of that exit area to our throat area, which we'll recall A star. So the assumption here is if the throat would be our choke area. So we'd be saying there the minimum area in our nozzle is 4,000 inches squared. So our area ratio, A over A star, is going to be 1.125. And now you're probably used to going to your isentropic flow equations, throwing in this area ratio, and determining the Mach number and pressure ratio. But here in this nozzle, we have to remember we're accounting for losses where there's friction and viscous effects, perhaps separation, and other things that are actually going to cause total pressure loss, which means we can't follow those nice isentropic curves that are assuming that the total pressure remains constant unless there's a shock wave. Here we're going to have a nozzle efficiency of 0.97. And of course we know gamma is equal to 1.35. And so in order to figure out the actual Mach number and pressure ratio that would result, we actually need to solve equation 5.2.8 in your book, which gives us this area ratio as a function of the Mach number at the exit, M8, but then it goes with a big function of gamma. Gamma plus 1 over 2 plus gamma minus 1. And we also have our exit Mach number in here. And that's going to be times our nozzle efficiency times 1 plus 1 minus gamma over eta n 1 plus gamma. All of that over 1 over 1 plus gamma minus 1 over 2 m8 squared minus 1 plus eta n. We need to extend that out. And that section is going to be raised to the gamma over gamma minus 1 power. And so ideally we would, if we have our computer, we would just do a nice iterative solution here to say we know A8 over A star, and let's solve for M8 because it's pretty difficult to invert this equation. But since we can't do that always, we also can resort to these nice figures in our book such as this curve, which is provided in figure 5.2. This is redrawn to make it a little bit easier to read. So we're interested in an area ratio of 1.125, which will fall on the left graph, left axis, right between our two tick marks. So if we draw a straight line halfway between them, that should be 1.125. And we don't have a curve for 0.97, so we'll use our closest one, a to n of 0.95. And we kind of try to pull out our intersections there. You see we'll end up with a Mach number, two solutions, of course. There'll be a supersonic and a subsonic solution depending on the back pressure on the nozzle. And so one's going to be kind of close to 1.4 and the other is going to be a little bit greater than 0.6. And so if we do a little bit more accurate solution and actually evaluate the numerical solution to our equation above, we would get M8 is going to be equal to 1.374 in the supersonic case, or it's going to be equal to 0.649 in the subsonic case. So there's always going to be some error reading a graph. We're not far off on these two, but of course if we can solve the full equation, we're better. So our next question is actually to solve the pressure ratio, the static to total pressure ratio that will occur at those two Mach numbers. Once again, you're used to, if you know your Mach number, you can look up in the isentropic flow equations this ratio of static to total pressure. But unfortunately, that's, again, for isentropic flow with a nozzle efficiency of 1. So with our nozzle efficiency of 0.97, we are actually going to need to use equation 5.2.6, which is the static pressure, P8, at the exit, divided by our inlet total pressure, PT6, is going to be equal to 1 over 1 plus gamma minus 1 over 2, with our Mach number at 8 squared, minus 1 plus our nozzle efficiency all over our nozzle efficiency. And that quantity is going to be raised to the gamma over gamma minus 1. Once again, we can simplify the solution process by looking at a graph of the results and pulling our values out. This one you could actually evaluate directly, but if we're looking at a Mach number of 1.374, we would come out here to just a little below 1.4 and pull off a line to our pressure ratio here, and these ticks on the left axis are about 0.04, so we're pretty close to a value of about 0.32, maybe a little lower on that axis. And then if we do the same thing for our subsonic case with a Mach number of 0.65, we can extract things here. We're a little below 0.76, so maybe say 0.75. And we'll see if we were to evaluate our ratio there based on the Mach numbers we calculated iteratively above and the a to n, we would get P8 over PT6 is going to be equal to 0.754 for the subsonic case, and the supersonic case is going to be equal to P8 over PT6 is equal to 0.32. And of course, with a total pressure of the PT6 equal to 10 psi, that means that our exit pressure P8 in this case will be 7.54 psia, and in the supersonic case, P8 is going to be equal to 3.2 psia. In order to know where we stand, we need to go back to the beginning and remember that at our altitude of 18,000 18,380 feet, that the ambient pressure would be equal to 7.233 psia. So that'll put us between the subsonic case and the supersonic case. Our exit pressure is a little bit lower than subsonic, but it's definitely a lot higher than the supersonic case. So that means we're going to end up with subsonic outflow, but that there has to be supersonic flow at some point in the diverging section. Basically, it's telling us that there's a normal shock wave occurring somewhere in the diverging section of our nozzle. And so the next question, of course, is, well, where is that shock wave? So the easy one to check is, what if there's a normal shock at the exit? So here we would be assuming that we started out with our converging diverging nozzle. We've got our subsonic flow in the converging section. We've got supersonic flow in the diverging section, all the way out to the exit of our nozzle, where there would be a normal shock wave standing that will take us from supersonic flow to subsonic flow. And so what we need to do here is look at our normal shock tables, and we know that the inlet Mach number to this normal shock is going to be 1.374. That's our Mach number for the supersonic case, because it's following this nice supersonic curve all the way to the very end. So we got a Mach number 1.374 going into our normal shock. And so for the normal shock tables with gamma equal to 1.35, we can look up our values for that Mach number and find that the outlet static pressure over the inlet static pressure is going to be equal to 2.0201. That's really equivalent to basically the ratio of our static pressure at P8 at the inlet to the normal shock versus P8 at the outlet of the normal shock. And so if we want to actually calculate the real P8, we're interested in P8 out, which is going to be equal to P8 in over PT6, which is a relationship we already found up above for the supersonic case here, 0.32. And then we're going to multiply that by this static pressure ratio, P8 out over P8 in times PT6. And if we check really quick, of course the P8 ins will cancel, the PT6s are canceling. So it would give us the correct P8 out. So we just take 0.32 times 2.0201 times the total pressure of 10 psia. So P8 out in this case is going to be equal to 6.46 psia. So we've moved up a ways from the supersonic pressure of 3.2, but we're still, our actual exit pressure to match this ambient pressure of 7.233 is still a little bit higher. So that tells us there has to be a shock wave occurring somewhere in the diverging section of the nozzle. And so we need to be able to figure out where that is. And so this can actually be an iterative process, because what we'll have to do is guess the area ratio that where this normal shock is occurring, and then calculate the resulting P8 out and see if it agrees with ambient conditions. And if it doesn't, then we would have to move our normal shock upstream or downstream, reevaluate the exit pressure once again, and see how see if it lines up better with the ambient conditions. So for our problem, we're going to guess that the area where this shock wave occurs, we're going to say that we're going to just guess a value there. We know that the throat is 4,000, the exit is 4,500, so we're just going to guess a cross-sectional area there, 4,200 square inches. And so once again then our area of our guess over the throat area is going to be equal to 4,200 square inches over 4,000 square inches is going to give us 1.05. So we just go back and solve our area equation here once again, or do it on the graphs, and we'll find that in this case the supersonic condition is going to give us a pressure ratio there, P at the upstream side of our shock wave divided by PT6 coming in. That static to total pressure ratio is 0.395, and our Mach number, we actually have to get the Mach number first, which would be 1.224, and of course use this Mach number in our pressure ratio equation here to calculate the static to total pressure. And so these give us the inlet conditions to our normal shock wave. So we're looking now for going back to Appendix E, our normal shock tables, and saying our inlet Mach number is 1.224. And so in that case, we would end up, if we go in with Mach 1.224, the Mach number downstream of that normal shock is going to be 0.8265, and our total pressure ratio at the downstream of the shock to the total pressure upstream of the shock is going to be equal to 0.9901. And so our next step then is we've got our Mach number. Because we've gone through a normal shock, we've changed our total pressure, and that means that we've got to account for the fact that the total pressure downstream of the shock now is going to be equal to 0.9901 times 10 psia, which will be again 9.901 psia. It also means that our area ratio has changed. A over A star. We're going to have a new throat area with this new total pressure, but we don't know what that, or not throat area, new reference area. We don't know what that reference area is going to be. So in order to figure that out, we would actually go back and put in our downstream Mach number of 0.8265 into our area ratio equation here. Putting in that Mach number for Mach 8, we calculate a new A over A star value there at this location. We can say A over A star is going to be equal to 1.022. Oops. And so our new throat area then, our new A star, is going to be equal to our area at the position of our normal shock divided by this area over A star. So 4,200 square inches over 1.022 is equal to 4,110 inches squared. So we've got a slightly different reference area here now that we've gone through that shock wave. And so based on this, that says that our area ratio at the exit of the nozzle, area of the exit over A star, is going to be equal to 4,500 inches squared over 4,110 inches squared at the reference area. So we're going to have an area ratio there of 1.0948. So we go back one more time to our Mach number versus area ratio equation and solve for the resulting M8. It would give us 0.685 as our exit Mach number, and then our going back to our pressure ratio equation and evaluating it at a Mach number of 0.865, we would find a total, a static to total pressure ratio of 0.730. And so we can finally say, if we're going to calculate our exit pressure here, P8 it's going to be equal to this 0.73 times our, really this PT6, it's our, we'll just call it the, we'll rewrite that as maybe PT downstream of the shock, which was, we figured to be 9.9901 psia. So we're going to do 0.730 times 9.901 psia, which will give us a final static pressure at the exit of 7.230 psia. And that is pretty close to our actual ambient pressure, which was 7.233 psia. So if you wanted, you could go back and move your shock wave very slightly, but this is pretty good convergence. If we were off a little further, we would slide our shock wave, our normal shock, towards the exit if we wanted to decrease the value of P8 that we calculate. And if we wanted to increase the value of P8 that comes out, we would move our normal shock wave forward, which would of course be giving us a smaller flow area at the shock position. So this tells us anyway that we have a normal shock in the exit that's occurring pretty close to where the area is equal to 4,200 square inches. And so we've got subsonic in the converging section, supersonic for the first part of the diverging section, and then after that normal shock we will be subsonic again. So from there, now we know the key parameters. We can solve anything else we need to know about the nozzle. So there you have it.